You check. Hello my dear, I welcome you in this session of foundation course. So, in the foundation course we already covered the two topics, that is first one the viscosity and viscous shear stresses, and the second one is your static condition, that means fluid it is in static mode, and in the static mode we have to discuss the hydrostatic force on the submerged surface like a curved surface and a flat surface. Okay. Now then we have to discuss this is the topic of the kinematics, and we have to the kinematics we divide by the two part 1 and part 2. In the part 1 we have to discuss the flow visualization, that means a flow pattern, that means a fluid flow description. Why the fluid flow description is required? My dear, see this one. Okay. So if you take the fluid kinematics, if you see the fluid kinematics, so why the question comes in our mind, what are the questions comes in mind? Kinematics of the fluid motion, that means why the description of fluid motion is required. Why the description of the fluid motion is required? In the solid we cannot describe the description. Why? Because see, fluid, if the fluid is moving and the solid is moving, so there are one demarcation between the movement of the fluid and solid. Solid have a definite deformation, but the fluid it's have a continuous deformation. That means it is not a very subtle, that means a very absolute deformation. No, it is a continuous deformation. Okay. That means description of fluid motion required because fluid, unlike solid, is not very simple to describe. Why? The question is that the reason is that the fluid is under motion is continuous deforming. That means each and every particles have its continuous deforming. Okay. So for the solid, if you identify the particle, it may be easy to track. That means for the solid particles you can easily track. Why? Because it is a definite deformation. But if deform the fluid, the tracking of the individual particles is very difficult. So let's so it may be easy to track the particles of a solid, but fluid it may not be easy to track the particles. So for the tracking of the individual particles, we have to required the description of the fluid flow. So let's suppose for the before starting the description of fluid flow, there are, let's suppose this is a fluid and there is a fluid particles, and we define the system. What is the system? System is a region in the space. A system, it is the certain quantity of a matter, a fluid, on which we have to pay the attention. So this is our system, and apart from the system, that is your surrounding. So if you describe the fluid, so we have to make a system, and in the system what the fluid characteristic will change, how the fluid characteristic will change, that we analyze by in the chapter of fluid kinematics. So my dear, before I start this fluid kinematics, I will announce something. What is that? Some features of IMS. What is that, beta? See, what is the features of IMS? See, this is IMS, that means there is a live, if you willing to join the live online program of 2025-26, so we have provide 800 plus hour live class with live interaction. Okay. Theory book, also we have provide you a theory book, exercise book, and in that exercise book 4,000 plus question. In that exercise book 4,000, all the variety, level 1, level 2, level 3 is there. Along with that 34-year GATE question bank with video solution, that have a very unique question, very difficult question to solve by your own. So we also provide the video solution so that you can easily understand. And in that gate book, there are two types of gate book. One is the technical, other is the mathematics. Both are the separate. Along with that, the unique features of IMS is that 12 personalized one-to-one mentorship session. That means you have a 12 personalized mentorship session, and you are feel free to connect any faculty what you have to required, that you have a personalized mentor like a doctor and patient. And 130 plus online test with video solution of and mock tests and many more. Now, if you want to counseling free, you can call this number. This number is 9663376248 or 7718815588. This is our number. So you can call free. Okay. Now, along with that, we have a Telegram group. And mind is, this is the very important one. To join the Telegram group channel today, to get, if you join this Telegram group, what you have to get, what you have to. Yes, others result आ गया sir, IMS से कोई, yes आया. We will make the video separately right now. Okay, that is the yes others. IMS से भी there is many more result is there. We'll announce. Okay, just now I will check that result. So this is the class. So we are taking the class. Other faculty will engage with that gathering of the. Yes, we have all the calculation. We have doing the calculation, and we make the one separate session. Don't worry others. We have make a separate session for that immediately. Okay, many faculty are engaging for that one. Okay, so if you join this Telegram schedule for, you have get a notification for the schedule, lecture PDF. You find a lecture PDF, important update related to the seminar and webinar, and also PSUs and other notification. You have expert session, important topic, expert session for the important topic, and also daily cues and many more. To join one, you have to join this Telegram group immediately. Okay, so that you get the many features. Okay. Now, come with that main content part. What is that? So my dear, if you want, this is very important lecture I am telling you. So if you want, so this is our system. Now beta, in the fluid kinematics, if you dealing with the fluid kinematics, that means a behavior of the fluid particles, that means you have to find the velocity of the fluid particle and also the acceleration of the fluid particles. So to study the fluid kinematics, there are two approach. First one is your Lagrangian description. Before I start with that beta, I will discuss something. What is that? So that you have to get a very good insight for that one. What is that? What is that, my dear? See, there are two things. One is the particle approach, other one is the field approach. So if you're discussing with the, this is very important, I'm telling you. This is very important things, beta. I want to share with you. What is that? See, my dear. See, this is very important. First, particles. This is a particle, and second one is the field, and that field is a continuous medium. Second one is your field, and this field is either scalar, vector. Okay, a scalar field is what? Density, temperature. These all are the field. That is your scalar field. And what is the vector field? Velocity field. That is the vector field. Okay. So this is your field. Now, let's suppose you have a particles. Okay, this is your particles of any mass m. This particles, and we want that this particle is moving with a velocity v. This particle is moving with a velocity v. How to describe? that means defined on the particle, that means this velocity defined on the particle. Defined on the particle, my dear. Now we want that force on these particles. So if you want the force on the particle, we must have go to the kinematic parameter. So if you want that force on this particle, so what is that? Mass of this particle into acceleration of this particle? Yes or no? Now, how to find the acceleration of these particles? You have to find the acceleration of this particle. To find the acceleration of this particle is equal to this velocity divided by this time, rate of change. So, in this one, how high, nu, high. So, this d, if you say that a particle approach, if you want to say that particle approach, so we want the acceleration, this acceleration is the kinematic parameter. So this d is your ordinary differentiation. Ordinary derivative. This is the particle approach. But if you defined the fluid, if you define the kinematics of the fluid with the help of field, so let's suppose this is your field. Let's suppose this is your field, either a scalar field or a vector field, and this is your axis. Let's suppose this is your x-axis and this is your y-axis. Okay. So in the field, we have to focus a region. So this is what we are. This is your space. This is your what we are. This is your field, and you have to focus one region in the space. You have to focus one region in the space. You have to focus one region in the space. That means region on the space. Region on the space. Region on the space. And this space region is defined by the kinematics parameter v, x and y. Why? Because this will v and x, y. So in this one we have to specify the region in the space. So this is damn sure this is a Eulerian point of view. Why? Because we are focusing a region in the field. Rather than in this one we are focusing individual particles. So these are the Lagrangian and these are the Eulerian. So in this one, if you find force, in this one, if you find the force, what is the force? Mass into acceleration. Now my dear, how to find the acceleration in the region of the space of the particles? Why? Because this region in the space is moving and a particle, this is your, this particle, in this one there is a particle. How to identify the particle of a kinematic parameter? So if you find the acceleration, this for the region of the space, so if we apply this force, this is for the region, this is for the region, this is for the region in a space instead of individual particle, instead of a particle. So instead of a particle, we have to identify the region in the space, and if you define the kinematic parameter, we define the partial. That means we have to define dou by dou x, dou by dou y, let's suppose dou by dou t. So this one is your partial derivative. So these are the partial derivative. So if we define the field, we are using the partial derivative. if you define the if you define the particle, that is ordinary derivative. And to connect in this between these two, this will connect in this. If you link with this between two, that is called material derivative. Material derivative. And this is precisely in the case of particle is a Lagrangian approach. And this is your Eulerian. This is your Eulerian. So the material derivative is a tool, mathematical tool, which will connect the particle to the Lagrangian field approach. So my dear, there are two perspectives. One is your Lagrangian descriptive. So what we have to do in the Lagrangian descriptive, this is your system approach. So Lagrangian is the system, that means a fixed mass. System approach, that means fixed mass approach. That means the mass is fixed. That means you identify a particle and that particle is fixed. And you are going through the particles along with the particles and tracking the path, you are tracking the properties. So in this one, this is a system approach. That means in this case, one second. That means in this case, my dear, it is visible, yes or not? So in this case, we have to describe my dear, we have to describe that is a system approach. That means the system approach. That means the mass is fixed. Mass is fixed, and also called particle approach. Particle. That means that you have to tracking individual particles. You are tracking an individual particles. Okay. So if we could track the individual particle for the description of the fluid motion, individual particles could have been a Lagrangian description of the fluid flow. That approach is your Lagrangian description. You have to track the particles. Now Lagrangian description of the motion follows a single fluid particles as it move about within the system. That means this is our system, and in the system the single fluid particles is moving. So my dear, we identify the single fluid particle with respect to any reference line, my dear, with respect to any reference line. So let's suppose this is our reference line. With respect to a reference line, this is the position, and the position is that means this particle time to time, that means at any time this is at here, after some time this particle at this point. So at the time to time this position of the particle will change. This position of the particle will change. So this is only depends upon the time. At what time we are tracking the position of the particle individually, and in this one we are bothering that where the particle is, from where the particle is coming and from where it is going. That means in this one we have to define the initial position, let's suppose this one, and then we have to track where it is going. That is your characteristic, but the initial point is fixed. That means if you defined R position vector, so this R vector is your R naught and T. So initially it is defined. That means you have to define this particle. Let's suppose we have to define this particle from here. After some time duration, its position will change, and you have to track the particle, define the velocity. That means the flow within the fluid system is defined by the tagging each fluid particles. That means individually particles you have to track and tag them, and then specify its velocity, acceleration as a function of time. So you have to describe this velocity, acceleration is the function of time. Particles move from one position to another position. So if you define the field due to this vector, if you define this field, vector field as a velocity field, this velocity will a function of time and initial position. The initial position is fixed, so it is generally it is defined by a time, and with this v is your dr by dt. So if you define the particle, let's suppose x direction, so u of x direction of the particles is what beta? D of x direction and by dt, and this x is the position is the function of time t. If you find the y direction, u of, so if you y direction v of a particle, that is the d of y dt by dt. So these are the particles approach, these are the particles. So this xy, it is the, this xy, my dear, this xy, it is a position vector, and this position vector is defined by the particles or the field. This is for the particle, not field. This is for the particles. So that is your Lagrangian approach. That is your Lagrangian. This x is not a field. This r is not a field. These are the particles. That means these are the particles approach. So these are the particles. It is defined as a particles. It is not a field. And if we define this particle in the field, we use the material derivative. We will discuss. Okay. Now, but what is the problem of this one? What is the problem in the Lagrangian description? In the Lagrangian description, the tracking of individual particles, the tracking of individual particles and describe each and every particle, and then you find the solution, that is a very difficult, that means very difficult to solve that equation. See, there is how many particles there, each and every particles have its own equation. Now you have to solve, that is the very tedious things. So this approach is not very practical. So what is the alternative, my dear? What is the alternative then? The alternative is your Eulerian description. And this Eulerian description, it is nothing, it is your control volume approach. That means you have to fix the space, you have to fix the region in the space, you have to fix the region in the field. That means this is a field approach. You are not bothering where the fluid it is coming and where it is going, only you have to fix the region, only you have to fix the region, only you have to fix the region. That means you are focused on the camera on the particular region and then see what is happening within that. So you see that what is the happening within this control volume. So this is your control volume, and then you have to define. So my dear, in this one beta, this velocity, how to define then? Then this velocity is defined by this one. That means here is the position. Why? Because beta, you can take any the particles. You are seeing a control volume, and control volume, and you are seeing the particles. What is the happening within the particles? So that particles continuously position change. Continuously position change with respect to time. So if you define the velocity field, this velocity field v, it is a function of not initial position, it is anywhere. That means you are focusing the camera, it is anywhere. So this is r and t, very important. This is very important. And what is in the case of Lagrangian? The case of Lagrangian, v is your function of t. Why? Because we are bothering about where it is coming and where it is going. So the initial position where it is coming, it is a fix. So we cannot take. So in this one, this is your things. Okay. Now, so Eulerian description, motion of a specified point or region. You have to fix the region within the system. So this is our system. Within the system, we fix the region and measure the velocity of the particles that passes through this point or control volume. Then you have to measure. So these are the field. This is called field, velocity field. This is a vector. This is called velocity field. Velocity field. So this vector velocity field is a vector field here. Field is anything, either a scalar or either vector, but it is here vector field, as also expressed in terms of Cartesian coordinate. How to express this one? See, this is very important. This V is function of x, y, z and t. Now this V is the, what is the V? V is what, beta? V is ui, vj, omega k, yes or not? Itself. Now this V and this u is in which, for which one? This is a field. So again it will depends upon x, y, z and t, all the term. So this V is the function of u and this u is itself function of x, y, z and t, I direction. This V is also function of x, y, z, j direction. This omega, that means z direction velocity, is also x, y, z and t. This is very important. So this, as this one, so someone write like that and you just ask you, this is your field or this is for the particle. So this is for the field. And the field have a Lagrangian approach. So in this one we have to discuss the partial derivative. So the relation between partial derivative to total derivative, the relation between the partial derivative and the total derivative, that is for one of the mathematical tool, that is called total derivative. Okay. Now see this. Then we have to start the material derivative. What is the material derivative, beta? See, this is your material derivative. Capital D by dt. This is your material derivative. And what they do? The material derivative, it is the, if we have a Lagrangian description, due to this material derivative, you can easily find the Eulerian description. Yeah, if you have a Eulerian description, you can easily find the Lagrangian description. So the material derivative, this is called a total, what is the name? Total derivative. Total material, substantial, these all are the, and if you write D here, if you, it is like that, D by dt, this is your signature of material derivative. Material derivative. Now if we write second thing, d by dt of anything here, anything, either it is your scalar field, either it is your scalar or either it is vector, that is your for the field, not for the particle. This is for field. Why? Because in the field there is a particle. So let's suppose the particle have a temperature T. Let's suppose field have a temperature different T, yes, same T. So the T will define for the field here. So always you have to write the material derivative. So differentiation of the total derivative is for the field, so that if we differentiate the result, it is in the form of partial. It is not in absolute. And this material derivative is exactly equal to the total absolute derivative, ordinary derivative, that means d of dt. And now, but here always write this is for the particle. This is for the particle. For particle. This is for the particle. So within bracket this one, this is for the particle, this bracket, this is for the field. Clear? And now we have to discuss also afterward RTT. RTT is the tool, Reynolds transport theorem, which convert the system analysis to the control volume analysis. This is your control volume analysis. This is your system analysis. So Lagrangian to description, in Lagrangian description to Eulerian description, the tool, it is your material derivative. System analysis to a control volume analysis, the tool is Reynolds transport theorem. We'll discuss this thing. This is very important slide. Now, my dear, we'll discuss something more in this one. What is that? See, what is that? Let's suppose we ask ourselves one question. What is that? If we follow a piece of a fluid, so piece of a fluid, what is that? Lagrangian. That means this is a piece of a fluid. And now you have to track this fluid particles. So you are tracking the individual particle, that means Lagrangian point of view. Okay. How will some property of this fluid, let's suppose the fluid property is temperature, density, anything. Some property of the particular piece of the fluid changes with respect to time. Now, my dear, this fluid particle, it is any field. It is this fluid particle, this is piece of the fluid, is present in the field. It's present in the field. So we are tracking the fluid particle, that means a Lagrangian, and we have to see what is the property will change after time will pass. So at this position, let's suppose it is time t naught, location x, or x is the function of t, that means a Lagrangian. Now after some time t plus delta t, the location is x naught, and you have to track. So if you draw this line, that is your path line. This is called path line. That means tracking of individual particle and seeing what is the locus of that particles, that is your path line. This is called path line. So my dear, path line is essentially the Lagrangian approach. Clear? That is the Lagrangian. So what is that? Let's say we are interested in looking the time rate of change. Yes, we have to looking the time rate of change of the temperature. Let's suppose we have to find that property temperature of the fluid particle after some time. That means let's suppose temperature of the fluid particle at the time t naught and at a location x naught, it is there. After some time t plus delta t, what is the location x, another x, what is the temperature of this fluid particle? Observe as it moves from location to location. The particles may experience a temperature change because of the temperature of the entire fluid may be changing with respect to time. Yes, this field, maybe let's suppose this field, entire field changes with respect, time to changing time, the temperature will change. Each and every location of the field, the temperature will change. So fluid particle also experience a different temperature at a different location. Okay, so particle may experience a temperature change because of the temperature of entire fluid may be changing with respect to time. The temperature field may be unsteady. That means the temperature field, the field is unsteady. Let's suppose the field is also changing, and field is also changing with respect to time, that is unsteady. So we are taking the field as unsteady. That means you are taking the steady also. You are taking the field is steady. That means the temperature is uniform. No problem. And what is the change of the fluid particles from location to location? You can say that. But we are taking a general case. In that one, the temperature of the fluid particle is changing when it is moving from one location to another location. Why? Because we are taking because the field of the fluid, the field of the field property of the field will also change location to location. Okay, so that field is unsteady field. Let's suppose the field is unsteady, that means the temperature field. So this temperature field T, this is a temperature field T, is the function of, let's suppose x direction, any x direction, x and T. So this T is your field, and this temperature is the function of T. This is for the particle. And my dear, this x is itself a function of time. Clear? This is clear or not? Please tell me. This is clear or not? This t is the function, this is a full field. T is the function of x and t. And for the particle, t is the function of t. Temperature is a function of time. So this is for particle. Now x is also a function of t. See, this is at t naught, and this x plus delta x delta t, x is equal to t plus delta t is at t naught plus delta t. So this is for the field. Field is a function of x and t, and x is also a function of time. Here, but t is the function of t, but t is not a function of position. Why? Because you are tracking the fluid particles and seeing what is the change with respect to time. So particles changing, we have seen the particle change. So change of the temperature T with respect to time. So this is for what? This is for the particles. This is for the particle. But this particle change with respect to T, yes. But the change of the particles with respect to T also experience the different temperature. Why? Because field have a different temperature. So we are converting this temperature of the fluid particle with respect to the field temperature will change. So that we will use the material derivative. So what is that beta? So thus there are two effects can be cause a time rate change. Yes, that effect is the time rate change of the temperature that a particle experience, that is the unsteady effect, also known as a Eulerian effect, and also the special gradient known as the convective. So this, if you do the analysis, there are two components. One is your temporal or local component, other is your convective component. These two combined effect gives the what is the change of the particles property. So how to do? Just see this one. Just see that, my dear. This is very important. So let's suppose, my dear, let's suppose particles, let's suppose the particles, T is the temperature, let's suppose T, this is the temperature, we have to define the field. So T is the function of x, any direction, x, one direction one, and this is a T. So my dear, this is a T, x is the vector, no problem. This T, so this is your field. This is your field. T is your temperature field. Temperature field. And this temperature field is anything, either vector field or either scalar field. But here by default, this T is the scalar form, scalar field. Scalar. Now my dear, this x itself is, and this x, this is for a field, and the position itself, also, the position itself a function of T, yes or not? So this is for the particles, this is for the particles, this is for particles. So essentially this is your Eulerian and this is your Lagrangian. Clear? So if you combine this one, this temperature field, it is a function of x, function of T and T. So this is your field notation. This is your notation of the field. Now if it is there, how to quantify the parameters? So if we defined this for the particles, let's suppose this is a particles, and these particles have a temperature T at any time T. So this particles will be changes after some time, it is reaches, and there is a position x is the function of T. Now after some time, this temperature is T plus delta T, and the position x is T plus delta T. Clear na? So these are the essentially path line. Now we have to develop the equation dt temperature by time. So this is what beta? This is for the particle. This is for the particle. We are saying the particle change in temperature. This is equal to, now this T is a function of itself x and T. So partial derivative of d by dt. So it is a partial derivative. Why? Because now, and it is at a fixed location at x. At x location, at a fixed location. So at a fixed location, we are seeing, we are focusing a region. We are focusing a region and see what is happening with respect to temperature. So essentially, this is your Lagrangian. Essentially, these are the Lagrangian. Why? Because we are fixed the position, we are fixed the control volume and seeing what is happening within that with respect to time. Okay. So T is okay. Now plus the temperature is also varying with the position. Temperature is also varying with the position. So temperature is also varying with the position dx. And now, my dear, x is the only function of temperature time. So this is your dx is by dt. Now, my dear, see, we have to put here partially. Why? Because temperature is the function of x and t both. So we are the temperature. If you differentiate the temperature, we put the partial. And if you differentiate the position x, but the position x is the only function of t, so we have to put here ordinary differentiation plus. Let's suppose there is a y also. That means this is, let's suppose this is x, y, z. Okay, fix the region. That means this is x vector. This is position vector. Okay, plus again dou t over dou y into dy by dt. Why? Because again y is the function of time only, plus dou t over dou z into dz by dt. Now, my dear, what is that? This is what? This is the velocity. This is velocity of a particle. This is the velocity of a particle. Why? Because this is a ordinary differentiation. So this is the velocity of a particle in x component. This is the velocity of a particle in y component. This is the velocity of a particle in z component. So these all are velocity of a particle. Now, so if we write like that, dt over dt plus u dou t over dou x plus v dou t over dou y plus omega dou t over dou z. Okay. So, my dear, this is your dt by dt, and this is for the particle. This is for the particles. Now if we split this one, that means here you have to write like that, dou by dou t plus u dou by dou x plus v dou by dou y plus omega dou by dou z into what? If you outside into t. Clear na? So this dou by dou t of something is a field. This is your field. This is your field. This is your field. So this is for the field. So all partial derivative, this is for the field. For field, and that is known as, this is known as capital D by dt. This total known as, and this is known as capital D by dt, capital D by dt, capital D by dt, and this here t is for the field. This capital T is for the field. That is your material derivative. That is your material derivative. So this is for the particle, but the partial derivative, this is for the particle, but this is for the field. This is for the field. For the field. That means we have to write like that, like that, dt over dt, and this is equal to dou t over dou t plus u dou t over dou x plus v dou t over dou y plus omega dou t over dou z. My dear, so and this is equal to dt over dt. So this is for the particle, this is for the particle, this is for the particle, and this is for the field. This is for the field. So if you write like that, d by dt. Now, one tool is there. What is beta? What is, if you write like that, dou by dou t of anything, okay, is equal to dy dt of anything plus, here we have to write u dou by dou x plus v dou by dou y plus omega dou by dou z of anything, any field. So this is your field. So this is for field. This is for field, This is for field, Now, my dear, what is this? This is what? This is what, my dear? Please tell me, this is what? Please tell me, this is what? This is your V dot del. What is V dot del? What is V dot del? There are very much more difference between beta V dot del and del dot V. This is V dot del, not very important, not del dot V. Very big confusion. Students say that, yes sir, okay, no problem, anything will write. No, I will just check. So, the material derivative d by dt is what beta? Dou by dou t plus v dot del. That's it. This is called material derivative. This is called material derivative. This is called material. If you multiply with any vector field, all multiply vector. If you multiply scalar field, all multiplication of the scalar field. So these are the notation. So you can write also like that, d of dt of anything is equal to dou of dou t of anything plus v dot del of anything. This is like that. This is the representation. This is the representation. Now, my dear, del is the del operator. What is the del operator? This is the vector operator. Del is the vector operator. What is that? See, it is like that. We will discuss this thing, no problem. So, this is your local. This one, this is your local. Yeah, temporal, and this is your convective. So total derivative, या material derivative, it is the combination of local derivative and convective derivative. Local derivative and convective derivative. If the and this is our field. So if the flow is steady, flow, that means field is steady, the local term is 0. Only the change of that field, it is only for only with the only the effect of convective component, not temporal or local component. Clear? This is clear, my dear? This is clear? Now, if we have my dear, let's suppose if you have any density field, let's suppose, before I start with the density field, let me know that one thing. What is that? See this one. Very important, I am telling you. This is very important. This is very important, I am telling you. What is that, beta? Important slide. What is that? Let's suppose there are two things. First one is, what is that, beta? First one is any vector field V. This is the vector field V dot del. Okay. So what is this one? What is this one? How to write this one? It is visible, na? Yes. How to write V? That means U V omega dot, this is del operator. How to write? Dou by dou x, dou by dou y, dou by dou z. Clear? Clear? Now, my dear, this is your vector, this is your vector. The product is a scalar. What is this? So if you solve this one, how to write this one? This you write u dou by dou x plus v dou by dou y plus omega dou by dou z. So these are the different thing. That means if we write this one like that, one second, change the color. This is very important, I am telling you. Okay, so what is this? What is this? Please see. What is this? This is your, it is like that, V dot del of anything, yes or not? V dot del of anything, and this anything is your what? Field. This is your field. This is your field. Now, so what is this? What is this? This is what represents. See, beta, this V is the velocity. So this V is the velocity component of, and this is your field. Any field is there. So this denotes the velocity of a gradient. This denotes the velocity component. That means the velocity in that direction. This denotes the velocity in that direction. In that direction, let's suppose u, in that direction of the gradient, that direction of the gradient of that direction of a gradient of anything, of anything for of the field, that means the velocity in that direction, the velocity, and this velocity is for the particle. So the velocity in that direction, which direction? Let's suppose the velocity u. So what is the direction of u? X. Let's suppose velocity v. What is the direction of y? Let's suppose velocity is u, omega. What is the direction? Z. So velocity in that direction of the gradient. This is a gradient, and this dou by anything by dx. What is that? Gradient. This is a gradient. So what is the gradient of the field? Let's suppose field is T. Let's suppose field is T. Temperature field is there. Let's suppose temperature field. So the gradient of the field, that means dou T. Let's suppose the velocity is u. Let's suppose velocity is u. So the velocity u, it is in which direction? X direction. So dou T by dou x it represents. That means this represents the velocity in that direction, velocity in that direction where you have to take a gradient of that field. Where you have to take the gradient of that field. Let's suppose the field is t, and let's suppose that gradient you have to take in x direction. So the velocity, it is in x direction. That is the meaning. Now this is first one. Now the second one, it is like that. See my dear, let's suppose second, point number second. If it is like that, del dot v. What is this one? What is this one? Del dot v. Del dot v is your, you have to write like that, del. That means dou by dou x, dou by dou y, dou by dou z. Dot, what is the velocity? U, v and omega. Okay. Now if you take the dot product, what is the result? This is your dou u by dou x plus dou v by dou y. You have to write like that, no problem. Here, what is that? Dou u by dou x plus dou v by dou y plus dou omega by dou z. Now my dear, what is this? What is this? This is what? This is what? Please tell me, this is what? This is your volumetric strain. And this is your, what is this name? What we have to call divergence of velocity vector. This is called divergence of velocity vector. So my dear, v dot del and del dot v not equal. See, not equal. This is like that and this is like that. Very good, very important thing is there. Now, so divergence of velocity field and the divergence of velocity field. So divergence of velocity field. So this is your divergence of velocity field. That means del dot v is equal to dou u by dou x plus dou v by dou y plus dou omega by dou z. And this is a divergence of a velocity field. Divergence of the velocity field. Divergence of the velocity field. Okay. Divergence of the velocity field. And divergence of a velocity field is what? Rate of divergence of a velocity field. What they said? Rate of volumetric strain. Volumetric strain. Rate of volumetric strain. Okay. And what is the rate of volumetric strain? That means strain, rate of a strain in x direction plus rate of a strain in y direction plus rate of a strain in z direction. This is a volumetric strain. Now my dear, and so the strain rate is what, beta? How to write this one? Volumetric strain. That means dou u by dou x same plus dou v by dou z omega z y plus dou omega by dou z. This is the volumetric strain. Okay. Now my dear, so if we write this, so this is a rate of volumetric strain. This is a rate of volumetric strain, yes or not? And this is your, in terms of, if you write in terms of total derivative. Oh, great, 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 great. Thank you, thank you, thank you. Rudra Mandir. Thank you, Rahul. Thank you. Very good, beta. Very good, very good, very good, very good. Very good. Very, very good, beta. I am also very good luck for your future, and I know that you got very much success upcoming time to time. Okay. So be patient and be motivated. Always you have to get a very good success. Okay, beta. That is good. Approximately you have to got 50 marks. What is the cutoff, beta? Cutoff I think 28 point something, na? What is the cutoff, Rahul? What is the cutoff? What is the cutoff, Rahul? What is the cutoff? You know any cutoff, Rahul? What is the cutoff of mechanical department? I think 28 point something. 1 second. Oh, yes, 28. Yeah, okay. Very good, very good. Okay, Rahul. So you got the admission, IITs, no problem. In IITs, you got the admission, no problem. Yes, 26 point something. Yes. Thank you. So, okay, beta. So this is a rate of volumetric strain, and that is a rate of volumetric strain. We'll also discuss for you, but okay, I know that you have any, if you want to something ask, you can please comment. Okay. So in terms of, write down, if you write the rate of volumetric strain in terms of total derivative, that means we want that the strain, it is continuous deformation along, why? Because fluid is continuous deformation along with the position as well as the time. So we have to find the in terms of total derivative. Terms of total derivative. What is that? That means if you write the volumetric strain in terms of total derivative, yes, you can do, no problem. Very good. You got admission, no problem. IITs, okay. Before, if you want to ask anything that sir, which branch or what branch, we are taking a continuous YouTube channel, so you can ask anything. Okay, I will give the reply. Okay, rate, that means in terms of total derivative, that means rate of change in volume to the original volume. That means rate of change of the rate of change in volume to the original volume. So how it will write? See, rate of change of volume. So dV by dt. Why we are taking total? Why? Because we know that position as well as a time effect. So we have to take total derivative. Okay. So rate of change, what is that? Change in volume in the form of rate to the original volume. Let's suppose the original volume V. So this is your volumetric strain. This is your volumetric strain. Now, if you have a density field, if you know this thing, then you have a density field. If you have a density field, my dear, okay, if you have a density field, let's suppose the density field, and density field is a scalar field, beta. Scalar field, density field is your scalar field, and what is that field? Let's suppose this field density is equal to x, y, z and t. Now, this is your which approach? Eulerian approach. field approach. Okay. Now, so if we write the total derivative d rho by dt, how to write it? D of rho by dt on a steady term, local term, on a steady term, local term. So this is for the field, okay na? This is for the field, my dear. This is for the field. So plus, now here del dot v. What is that? See, here we have to write del dot v, not v dot del. Here we have to write del dot v into any vector field density, scalar field density, like that. This is your operator. This is your operator. See, this is your operator. D by dt of anything density is equal to d by dt of density v dot del on density. And v dot del, how to find v dot del? So v dot del you have to find v dot del is like that. Okay. Now, so v dot del. Now, this is how to split. That means, my dear, this is what? This is at a fixed position. That means x, y, z fixed, and we have to differentiate with respect to time. So this is dt. Now this is for the field. This is all for the field. Now, and if we write this is equal to d rho by dt, so this is for the particle. 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 Now, you have to split it. So, d rho by dt is equal to dou rho by dou 2 at a fixed position plus, if you split this one, so this is your u d rho by dt plus v d rho by, no sorry, this is your y x plus v d rho by dy plus omega d rho by dz. Clear? This is clear? Now, so this is for the field. This is for the field. Now, my dear, so this is okay, this is okay. Now, so this is for the field you have. Now, my dear, we know that, let's suppose there is a density of any mass rho. So density is what, beta? Let's suppose, here we have to write, let's suppose mass of the body m is equal to density into volume. Now, we want that the volumetric strain, we are focusing about the volumetric strain, and volumetric strain is your dv by dt 1 by v, and that d is your total derivative. So we want that the derivative is denominator, so we must have to take the log. Sometime interviewer asks why you are before you deriving, why you are taking a log. Motive is that we want that v is lower, downside. So if you take the log, so log ln m is equal to ln rho plus ln v. Now if you take the log, so this is 1 by m dm by dt is equal to 1 by rho d rho by dt plus 1 by v dv by dt. Clear now? Now the mass is fixed. So this is 0. This is 0. Why? Because fixed mass. Fixed mass. Okay na? Now, so this is 0. That means what is the fact is that means 1 by rho d rho by dt plus 1 by v dv by dt, this is equal to 0. Yes or not? Yes or not, my dear? Now, this is what? Rate of volumetric strain, and rate of volumetric strain is what? What is the rate of volumetric strain? Del dot V. Del dot V, divergence of a velocity vector, del dot V. So, this is your divergence of a velocity vector. So, what is that beta? 1 by rho d rho by dt plus divergence of a velocity vector is equal to 0. If you write that density, if you take like that, so d rho by dt plus rho del dot V, and that is equal to 0. Clear now? Now, what is that? We know that this thing d rho by dt is what? Dou rho by dou t, and this one. Yes or not? This you know that. Put the value here back. Put the value here back. Put the here value back. So, d rho, that means dou rho by dou t plus, this is what? You have to write like that. Del dot V into rho plus this thing. This thing is what? This is what? This one. This d rho by dt instead of here. This capital D rho by dt is what? Small d rho by dt, dou rho by dou t plus this one, and plus this right term rho del dot V is equal to 0. Clear na? Clear na? So, how to write this one? That means, if you write my dear, that means what is the equation? Dou rho by dou t plus V dot del rho plus rho del dot V. Del dot V, this is equal to 0. Now, my dear, if you club this one vectorial form, this is your del dot rho into V vector. Just put this value, combined it, you got this one. So, this is your d rho by dt plus divergence of this V vector is 0. This is called continuity equation. This is called continuity equation. Continuity equation. This is called continuity equation. You can easily find that continuity equation. So, my dear, the moral of study story for the today is what is that? This is the main thing which you have to understood. Why? Because 90% student get confused V dot del and del dot V. Both are the different things. Okay. So, if you take the total derivative, this term is coming. If you take the continuity equation term, this term is there. Why? Because for the incompressible fluid, this is your compressibility. That means this says that the volumetric strain, divergence of a volumetric strain. So, for the fluid, if it is incompressible, there must be a volumetric strain is 0. That means del dot V is 0. So, in the case of, if you take a total derivative term, this term will come in. This term is come when you take a total derivative. So, d by dt, if you are taking d by dt, this term is coming. If you are taking the continuity equation, this term is come. So, this is in the continuity equation. Continuity equation. That are the very important thing which I want to share you for, so that we take this session, and this session is very helpful for each and every student who got confused at this point. I know that at that point the many students get confused. Okay. So, I hope you like this session. So my dear, if you want to know that this such type of concept, if you want to know that, you are willing to know that I want that such some subtle concept is here, please subscribe my channel, video channel, YouTube channel for the IMS, and try to press the bell icon so that you get the proper notification and proper updates. Okay my dear, thank you, bye bye.